This week I began making an exit for finishing reading Mendelson. I read the appendix on complex numbers, Appendix G, and then also I read a few more sections of Chapter 5. Very long, so actually this is not, look at how quickly I went through these chapters, but boy, there's a lot in here. So that's my reading. And I'll show the book briefly, but also mention because it's within the context of mapping back to Rudin. So in the case of Chapter 5, it's really when we finally bring it home for the real number system. And so, of course, as I said in the last video, it does map fairly well to Chapter 1 of Baby Rudin, but then towards the end, this author, Mendelson, actually chooses to use the Cauchy sequences and Cauchy completeness to build the real number system. So really, it's all an elaborate mapping of an ordered field, an arbitrary ordered field, and then the ordered field of the real numbers, which is Cauchy complete. So the theorems are really setting up bridges between all the theorems for an ordered field and then the theorems for Cauchy completeness. That's really what he's getting at. And then once he finishes that in section 5.6, Cauchy completion, then section 5.7, which I've started reading, is really basically a victory lap of saying, okay, now that we have the real number system, we have arrived at the top of the mountain. And so there's really three sections: topology, and then which I haven't started reading, continuity, continuous functions, ending with infinite series in section 5.9. So that's going to finish off the book for reading. But then, of course, there's a lot of problems that I haven't done, and I plan to go through these problems. I'm not sure how many of them I will do, but definitely Chapter 5 problems are going to be important for me to do. And I love doing problems, and it's something that I have found a little frustrating about the way that I've done this project, but I'm learning and I'll adapt eventually. But I think there's going to be a point where I go from massive reading to massive problem doing. And so one of the things that I like a lot about these latter sections is how Mendelson does what Rudin also does. And I think also in Bardo and Sherbert and Wade, all the analysis books do this in a different way. And I find this most interesting, that all these different concepts that build to uniform continuity are built in different ways. Sometimes the theorem is put in a major statement that has equivalences, and sometimes, and I think in the case of Bardo and Sherbert, he did that, he'll go through and build these one by one in separate theorems. It's 6 of one and half a dozen of the other. But boy, I think if I have the time, I love to do a comparison of that. So then back to my notes, or onto my notes, I should say. This is where I left off last time. I put a little marker here for that very reason. Then, yeah. So I kept on reading, as I said, for Chapter 5. And he slowly built up all the theorems in an ordered field in Chapter 5. The Archimedean property. Where is this big theorem? Let me see if it is in here. Then limit theorems, of course, which we are all very familiar with. Yeah, so before he gets to this, there is something that I think I may have presented in the last time that I showed my notes, which is earlier in Chapter 5. Let me see if I don't page too much to get to it. But it's a four-way equivalence that is built up. Let me see where it is. If I don't find it, I'll just keep going. I'll come back to it. But there's a four-way equivalence for an ordered field. Either way, this is very important, of course. So if you get convergence, then you can get to Cauchy by theorem 5.3, and you can get to bounded by theorem 5.5, and then from Cauchy you can go to bounded from theorem 5.4. But notice these are all one-way streets. Yeah, all one-way streets. Here we go. This is the theorem that I was looking for. I always go the wrong way, and I should have thought about it before I made the video. I apologize for that. And so yeah, for any ordered field, the following conditions are equivalent. There is completeness of the field, monotonic functions, then the field is Archimedean and has the nested set property. Then it's also Archimedean, but it has Cauchy completeness, and you go from completeness to monotonicity, I think is the word, then to Archimedean and nested, then Archimedean and Cauchy complete. Beautiful theorem. It took me a really long time to read, but I love to sit down and just go through when something this fundamental is laid out and map it and then go through very slowly. This took several hours to read through, but I wanted to make sure that I did that, I think, in what I would call correctly. Yeah, and every now and then I'll go back and put it in just so that I understand where we are in that mapping. Then, of course, an equivalence relation for the two series arrive at the same place. And then, of course, this is the money theorem, which is Cauchy complete field is a field. And, of course, the C sub f is the set of all equivalence classes with respect to two series arrive at the same point, which is that equivalence relation. Beautiful here how all the field axioms are proven for this field. So one thing that I really like about reading this book, I think this book has just yielded a lot for me, is that you really get into a rhythm of playing with the field axioms and proving all of the field axioms for something. Okay, so here you go. Then this field is an ordered field, which is kind of the conclusion. Equivalences for Cauchy sequences. Yeah, C sub f is Cauchy complete. There it is, with sub-proving, which I thought was very interesting the way Mendelson did it. So there's really the prove, and then there's a sub-prove and another sub-prove. And I really love the way this book uses Archimedean. This is something that I think in Rudin is dropped on you in a single theorem, the Archimedean property. In the case of Mendelson, I really like that this book uses the Archimedean property explicitly in proofs. I found that very elucidating, useful. And then the Appendix G for complex numbers goes through some axioms proven for complex numbers, and the complex field axioms are also proven within the text of chapter 5. Where was that? Well, I guess it is done in Appendix G. Yeah, there they are. And this is the same that is done. This is also done in Rudin. Yeah, right here. This is also done in Rudin, the complex field and the field axioms. And some of the basic properties of complex numbers also done in Rudin. And yeah, even though this book, Mendelson, is a really good companion for as a second proofs book, this book actually fits exactly where I used it. Because I think if you really did this book in gory detail, Lawrence series, page 219, you would come to a point in the book where Yes, you can ignore the fact that they're talking about Lorentz series in one of the examples for a problem, which I would love to do. I think I plan to do this problem when I get around to it. But I think it's a good idea to know what Lorentz series are. So this is why I believe that this book on number systems really fits after a first course in real analysis and complex analysis has been undertaken. That's my understanding. And so here a set F minus a set W, and the set W is the intersection on a bunch of sets. This is where for covering subspaces and spaces. And for some reason, I really couldn't get it. I couldn't understand it really by doing sets as well until I did just two. And so of course, when you take out the W, you get that. But that's equal to taking F and taking a whole C1 out of it, taking a whole C2 out of it, and adding them. And when you add them slowly, as you add more, you keep getting overlaps, but that hole in the middle remains. And this is why F minus W is equal to the union of all the F minus C's. Yes, and that, incredibly enough, that actually took me a good 20 minutes to like go, okay, how do I do this? I kept doing it wrong. Yeah, and this is yet another one of those equivalence theorems that I love, because I love going through long theorems and just sitting down and spending a couple of hours. So yes, theorem 7.6 was like that. The ordered field F has the following equivalent properties. F is complete. F has the Heimborel property. F has the Bolzano-Weierstrass property. And so proven in that order. Yeah, and this is also done in Rudin, but in a different way. And again, this is why I was saying before that I wanna get around to comparing how all these books have done it. So in the case of Rudin, it's done for R to the n, and it says E is close and bounded, which is Heimborel. And of course, Rudin, in his own very cryptic way, mentions that in the page before. Then E is compact, and every infinite subset of E has a limit point in E, which is the Bolzano-Weierstrass theorem. So yeah, it is done in Rudin, but look at how brief it is. And in the case of Mendelson, because I am a baby, I love the way Mendelson did it, and it's a long proof that took several hours to read with a lot of steps in between. Yeah, and it ends right here.